So
Thank you very much.
we'll monitor the questions online.
Can we do a sound check? Can everybody hear me okay? Got a yes? All right. Thank you, Adam. All right. I got 3 degrees. I spent a decade in college. My bachelor's is engineering, my master's is geology, and my PhD is geophysics. And for the most of my career, I have worked as a professional geoscientist. I worked geothermal energy exploration on the Pacific Rim. I did some engineering geology. I did gold exploration in Venezuela. I did coal bed methane development in People's Republic of China. I spent a little more than a decade doing water resources development here in Kern County. And I did some ground penetrating radar surveys, about 60 of them for Chevron over on the west side to look for buried oil field hazards. And for the last 15 years, I guess, in my spare time, I've done resistivity and thermal property surveys for power plant constructors, and that's pretty much what I'm going to talk about this afternoon. So you can see that I'm not very good at holding a job, but it's been interesting. I am an armchair astronomer. This is my observatory. I photographed the transit of Venus and the 2017 solar eclipse. It was all fun. I'm an armchair guitar player. I met my hero, Tommy Emmanuel, a few years ago at a concert here in California. And every time I go to a job in the Tennessee Valley Authority area, I always fly to Nashville, and my first stop is Carter Vintage Guitars. The last time I was there, I played Doc Watson's Martin D45, and actually I like mine better, but his had a price tag of $250,000. And I think that in the course of a half hour, I played $1 million worth of guitars. And so it just made me better touching them. I point that out because if you travel in your work, I recommend that you take the time to avail yourself of things that are in the neighborhood. I'm a homebody also. This is Mozart, and there. And I get artsy smartsy every so often out in the front yard. I'm also an engineering geophysicist. Actually, I think my degree says geophysical engineering, still a semantic difference. These 2 guys and I are my field crew. We've worked together for at least 20 years. I'll tell you a little more about that on the way. Okay, so this talk is about problem solving. And in the electric power generation industry, excess heat can be a problem. The solution is heat management. And heat management is engineered in the design phase before anything is constructed. And so I provide relevant thermal parameters, but there's a snag, okay? So buried cables are always at risk of overheating, and the soil surrounding the cables insulate and prevents heat loss. And so the cable systems must be engineered to prevent meltdown. But there's a problem in determining the soil thermal properties, which I'll get to, and that's part of the research. First, let me give you a little background about electric power and how I got here. So just here's the learning segment of my presentation. Power and energy are different, okay? Energy is the substance that has the capacity to do work. And energy is a quantity measured in joules, whereas power is the rate at which energy is delivered. And it's measured in joules per second, like miles per hour, gallons per minute. It sounds like a rate because there's a time in the unit, but It confuses everybody because we call power watts, and it sounds like a quantity, watts, but it's not. It's a rate. The wattage is the rate at which energy is being delivered. Okay, it'll be on the next quiz. Watt is not a quantity, it is the rate of energy delivery. And you'll see on the following slides that everything is unitized by wattage, not energy. And it's the average rate of energy delivery that all this is talking about. Okay, so what are these facilities? A power plant generates electricity, electric energy. A high power transmission system conveys that energy to market. That's how they all work. And in 2025, the continuous average electric power usage was, in a couple of different contexts, an average American household uses about 1.25 kilowatts, thousands of watts of power continuously. That's the same as your toaster running nonstop, okay? So not all that much. All American households are about 156 million kilowatts, and that's about a third of the national power consumption right now of 480 million kilowatts. And 468 million kilowatts is the same as 468 gigawatts. And a gigawatt is a very big unit, but when we're talking about large energy systems, it's a useful unit to talk about. The wattage is the continuous average rate of energy delivery. It goes to residential, commercial, industrial. That's pretty much it. And as of 2026, there were 12,500 utility scale electric power plants, mostly consisting of smaller facilities. There's one power plant per 300 square miles, roughly, in the United States. There are actually less than 200 gigawatt scale electric power plants in the country, but that's changing. There's a strong demand for more electricity. And the new residential, commercial, industrial power demand is quite small, but new data centers, power demand is 95 million kilowatts in the next 4 years. 95 gigawatts of new power generation, or 950,000 acres of utility scale solar farms, or a continuous 5-mile wide strip of solar panels all the way from here to Sacramento, almost 1,500 square miles. You know, every time you click on AI, you just think that cha-ching, you're building a new power plant. So what's the response to the demand? Build more generation facilities, use up acreage. And this is relevant. Solar is relevant in the San Joaquin Valley, and not everybody is aware of the connections, but we've had a lot of drought conditions since 2000, and farmers who do not have secure water supplies have been basically getting out of the farming business. And the best way to get out of the farming business is to sell it to somebody who needs land. So we're taking farm acreage that just hasn't got enough water in the last few years, and we're turning it into solar farms. The most productive farm acreage on the planet is going into solar farms here in the San Joaquin Valley. There's combined cycle natural gas, which is still conventional power plants, the new conventional power plants, which are quite efficient, and then wind. Of course, the combined cycles still have a carbon problem associated with them. So for my part, every new facility has a grounding system and underground power cables, and that's kind of where I come in. I measure the earth resistivity for grounding grid design, and I measure soil thermal properties for buried cable design. And so let's talk about resistivity. Grounding grids. Every electrical component of a power system needs to be grounded so that no one gets electrocuted if a problem occurs. And since power systems cannot be shut down instantaneously, electric current is diverted into the earth through the grounding grid. And a grounding grid is literally a mesh of buried copper wires that dissipates electric current into the earth across a large area. Schematically, it underlies the whole power plant footprint, and they're laid in by trenching, just like that you see on the right. So the engineers that design the grounding system have to make sure the grounding system is capable of a couple of things. It must be robust enough to handle the maximum amount of conceivable electric current that needs to be dissipated into the ground. And then they also need to assure the operator that no one will get electrocuted in such a situation. And so you have to build a big grid to get rid of a lot of electric current. And the bottleneck is the resistance to ground. The capacity of a grounding grid to safely handle current depends on the resistance to ground, and the resistance to ground is a function of the grid size and the earth resistivity, which is a measurable property. So here's the formula right out of the IEEE standard. And the resistance to ground for large power plants must be very small. The RG, the resistance to ground, must be less than a half ohm. And according to this formula, it is directly proportional to the earth resistivity, a measurable property, and that geometric factor there that basically is a function of the grid size. So in order to get your design parameter for a given resistivity value, this grid factor here, the higher resistivity is, the lower that the grid factor has to be. And the way you lower the grid factor is to just make it bigger, basically. So this is a way of figuring out how big the ground grid has to be based on what the earth resistivity is. So I got started around 2004 in this business, thanks to Tom Bain and Bob Becker at Soils Engineering here in Bakersfield, by providing Schlumberger resistivity soundings to help power constructors design safe grounding grids. So we use the worldwide standard Schlumberger geophysical method to collect the data. I then invert and interpret the data to determine the true resistivity versus depth profile beneath the site. My crew consists of my two good friends, Doug and John Goodwin, and me. We travel all over the country at the request of clients to measure resistivity of the earth at new power plant sites. Sometimes we're there when construction is ongoing. So we lay out cables, we put electrodes into the ground, we wire them to a measurement system, we take dozens of readings, and then I do an interpretation and write a report. And so this is the primary deliverable product of a resistivity survey. It's the variation of resistivity versus electrode spacing, and the shape of this curve is a function of the resistivity layering in the earth. And so I process that to determine the resistivity versus depth profile, which is on that right graph there. And that is the product that the grounding grid design engineers use to figure out the resistance to ground. Okay, now thermal properties, kind of what my talk is about, sort of. Around 2013, a client asked if we also did thermal properties tests. And after spending 14 years in the geothermal energy business, heat flow was kind of an acquired expertise. So after thinking about it, I said yes. And so Doug, John, and I started doing thermal properties testing as well. Here's a typical situation. This is a client map of a 3x3 square mile area in Ohio, and the X's are the exact locations where they wanted me to take thermal properties measurements. And so we go out there with our GPS and our resistivity equipment and our thermal equipment and take the readings. And I'll skip that. So here's what we use. We use a thermal properties analyzer. This is a nice handheld $5,000 piece of equipment. and a variety of thermal probes, and they're $500 a crack. So every time I bend one of those, it's like $500 out of my pocket, okay? And if you're poking that into cobblestone soils, you know, I can get upset really easily. Okay, actually, it's not all that bad, but you have to be careful. So this is the equipment. It's all it takes, really. And we were on an Ohio solar project, and we conventionally take our readings at a depth of 30 to 36 inches. And so we talked a local farmer, well, we paid him, into using his tractor auger to drill the holes for us. And then we do the thermal measurements. And to us, this is great fun, okay? It is kind of out of the ordinary. And on a Texas solar project, we talked the client into letting us use their trencher. The same thing. We trench down to 30, 36 inches, take our thermal readings, and we're done. And at a Florida power plant, most of the time, this is pretty typical. Doug and John dig the holes, and I take the readings. Easy peasy, right? Anybody can do this. And in fact, that's true. This is the geotechnical work. And if you're a competent worker, you don't have to know anything about thermal properties to do this. It's not quite that simple. There are lots of things that can go wrong when you poke that probe in the ground. And so, but it's technician level work, frankly. And the three of us are just suckers for going all over the place doing this stuff. All right, so whoops. What'd I hit? So this past year, we did another job for a new solar plant in Ohio, and we actually had to wait till they harvested the corn and the soybeans before we could get into the work area. And then this past summer, Jose Gonzalez from the department here joined the field crew for a week, and out in the 114 Fahrenheit solar heat of the Mojave Desert, we did the same thing. We dug holes and took thermal readings. And we used the canopy, you know, for obvious reasons. It was hot. And the protocol is on this work is that when I do the measurements, the diggers get to relax, okay? And of course, when they're digging the hole, I get to relax. So it kind of works out. In Texas this past year, we had a job site in which they wanted our readings to be 15 feet under the ground because they were going to level it and remove a lot of earth. So, but they wanted their thermal measurements, you know, before any of that got started. So we had this excavator dig these deep holes. We were 15 feet below the ground surface taking our measurements. So every job has its little twists, kind of. Doug, John, and I typically do 3 to 5 projects a year. It takes about a week, okay? So 3 weeks out of the year, typically, I've got to find a window where I can get away and do this. And the white dots are recent jobs that I've been on. And it may not look like there's a trend, but starting in the New York City area, you see an arc of white dots that heads down to Louisiana, and that's basically the Ohio River Valley joining the Missouri River, joining the Tennessee River, joining the Mississippi River. And why is that? It's because a lot of these power plants are next to big rivers because they need the cooling. And then out in the west, which is a different thing altogether. But anyway, this is where we've been lately. And the 3 red dots are 3 projects so far that I've been asked to work on this year. The dot up in Idaho is at the Idaho National Laboratory, and it's a small, high efficiency prototype nuclear power plant. And the red dot in Pennsylvania is Homer City, Pennsylvania, about 50 miles from Pittsburgh. And look at the size of that plant, 4.5 gigawatts. That's 4.5 times bigger than your typical large power plant, and it's entirely for an AI data center, completely. And this is one that I've just been talking to a client on this week. Astoria, New York, the CHPE substation. This is the Champlain Hudson Power Express. And this is kind of novel. Hydroelectric power being generated in Canada is coming down to New York City by a buried cable that goes down the bottom of Lake Champlain and then is connected to the Hudson River. And it comes down the Hudson River and it comes up at the East River at this substation where it's converted from direct current to alternating current. And it's a little bit over a gigawatt. And so that's pretty novel. And I'll get to work on that. All right, so here's when the research started. In my opinion, as a geoscientist, there are 20 dots on this map, but to me it looks like it's undersampled. And why do I say that? Because I know from my experience as a geologist about the natural variability of soils, okay? And so if these are like a quarter mile apart or a half a mile apart, or and if they're placed in exactly these locations because the engineer wants the number for an electrical facility that's right at that location. We're serving his needs, but we're not necessarily measuring what needs to be measured to get a good representation of what the thermal properties are of the underlying soil. So I was concerned about undersampling, and here's kind of a schematic way to think about it. But I will say electrical engineers know very little about soils or natural variability, and they typically don't ask these questions. They think that when somebody like me comes up with a number, that is the number. Okay, they really, this is not their area of expertise, so they don't think about natural variability. So the black line is a hypothetical path of a buried cable, and the colored dots from dark blue, light blue, green, yellow, and red represent hypothetical measurements of thermal properties from low values in the north to high values in the south. It looks like there's a trend there, okay? And so the engineer will struggle with this because he doesn't really want to define 5 different cable structures to handle the different thermal properties, but he knows that if he designs for the worst case, which is that red dot down at the bottom, then he's over designing for the whole rest of the cable run, and it costs a lot of money to do that. Well, this data set of 5 points might make a person think that this is how the soil structure should be represented. This is not a cross section, this is a map from north to south. So we start in a soil that has a low thermal conductivity or thermal resistivity, and then it gets a little higher and a little higher, a little higher and a little higher to now we're in the red zone with high thermal resistivities, which means poor heat dissipation, okay? So how do you design for this? Do you install cables that get successively bigger and bigger and bigger and bigger to handle this, or what? Well, that's not my job. My job is to try to tell the engineer what I think is going on below ground. Okay, I'm the geoscientist, not the electrical engineer. And so another possible thermal model is this. And that is the exact same data from the previous slide with the exact same statistical variability, but completely random. And I think this is what's going on. And it just so happens that on that previous slide, I got a blue dot out of here and a green dot out of here and a yellow dot out of here and a red dot out of here, only because of just the way the sampling happened to turn out. If I had repeated the survey, it might have come out completely different. But nobody does that. I can't say as I have competition, but I do know that there are other people doing these measurements. because my clients are sending me their data sets all the time saying, what do you think of this? And you know, it sounds like poor professional practice to say, well, I don't think they did a very good job, and here's why. And so how do we tell the difference between the previous model and this model in an undersampled project? And to me, the answer is very simple, and it comes out of my background. Where's the next slide? Oh, sorry. Right. My solution is to simply take multiple thermal resistivity measurements at every location. I didn't build a slide for that, but I now compare the within location variance to the between location variance. And so far, the local natural variability has been larger than the project-wide variability, which tells me that if you, I guess my online audience can't see me pointing at the screen, but you pick any spot along here, and it's pretty unlikely that there's more than 2 or 3 squares of the same color, which is just telling you that there's such a high variability along that line that that oversampling is the best antidote to not knowing what's going on. And the statistics have told me conclusively that this is probably the better model for the thermal distribution in the project area, and that they should frankly design for the average thermal property, not the low or the high. But that's not up to me because I don't do the cable design. Everybody has risk aversion at different levels, so you have to design accordingly. Okay, so around 2020, a client asked if I could perform thermal dryout tests on some samples, and this was new to me. There were no established standards. I looked, and so I researched it before saying yes. And here's what's going on. Here's a little schematic. We're looking at a cross-section of the cable, which is the black dot, and then there's an area surrounding the cable where the heat is being dissipated into the soil. And the buried cable engineer must provide a cable with sufficient ampacity, as they call it, to carry the required current. And they must over-design the cable because the cable resistance goes up as the cable temperature goes up. And the engineer must further over-design the cable due to the insulating effects of the surrounding soil. If this were a cable hung in the air, like a normal transmission system, heat dissipation wouldn't be a problem. But when it's underground, it cools off much more slowly. So they have to over-design for these factors. And so what if the thermal resistivity is not constant but varies across a project site? Will the engineer need to design different cables for different soil types? And so what's missing in this analysis? And so the dynamics, as I visualize it, is that if cable heating drives water out of the soil, the thermal dryout curve, which I guess I should have described, well, it tells the engineer how much thermal resistivity will change, which can be factored into the cable design. If the soil completely dries out or gets below the critical water content, the thermal resistivity will be very high, requiring very expensive cabling. So the engineer has limited options: design for the worst case scenario, design for different cables for different soils, which is also very expensive, and use a backfill material that will not lose its water content so as to remain with a low T row. So the thermal dryout test is not a field test, it's a lab test. And we collect a sample, which is in that tube there, and we test the thermal resistivity at multiple different moisture contents, which means that I have to treat the sample between readings to change the water content. And the graph is the deliverable product. Now, this is from the IEEE standard, and this table just shows some representative thermal dryout curves, and the water content of the soil sample is plotted on the x-axis, 0 on the left, which is perfectly dry, up to about 20% water content on the right. And the thermal resistivity rises up the y-axis. And you'll notice that the thermal dryout curve of a uniform sand has pretty low T rho values, whereas the clay curves are significantly higher, and then there's things in between. All right, so what does this tell us? It just tells the engineer that for a particular soil type, if you know what the water content is, you can read up into the graph and kind of get an estimate of what the thermal resistivity might be. And actual data will be plotted on the same kind of plot, and you can read that for specific soils. Now, what soils are we talking about? There's two different cases that I have to deal with. Buried wire installations are one of two types: cables inside a buried duct bank or direct buried plow-in cables. In both cases, the insulating effect of the soils retards heat loss and the cables heat up. And so I measure the thermal properties for the electric power engineers. So the duct bank is surrounded by a compacted engineered fill. So we have to take the soil, left picture, and put it in a Proctor mold, compact it to the right density, then measure the thermal properties, and then boom, we're done. I write a report. But for plow-in cables, the test must be done on native soil, collected at the proper density and moisture content. And so it's usually collected in a Shelby tube, and it arrives at my company's international headquarters, which is my wife's garage, where I take all these measurements, and we test them like that. All right, so I'm going to skip that, just some data. And okay, well, this is a thermal dryout curve. And at 0 water content, you'll see that the dots are at a thermal resistivity value of about 600, which is quite high. But as water content increases beyond about 5 or 6%, the thermal resistivity comes down to a quite low value, and it remains low out to full saturation of the sample. And so the electrical engineers want to make sure that their soil moisture content stays in that lower range, so we don't have any very high thermal problems. We know how the thermal resistivity changes as the water content changes, because that's what's on the graph there. But we are unable to quantify to what extent the soil water content will change due to the heating. So we know what the thermal resistivity will be at a given water content. We just don't know what the water content will actually be under operating conditions. And so this means that for some soils, we do not really know the steady state conditions that the engineer must design for. This is the snag. So I have some ideas about the types of tests that we could perform to try to quantify the heat-induced mobility of soil pore water. And with our research affiliations with Lawrence Berkeley and Lawrence Livermore, it might be something that our geology students could investigate in the future. And so, guidance and takeaways. I want to extol the perks of working outdoors with friends. I want you to be conscious in your career and with your colleagues that whatever you do it with people that you have fun with. It just doesn't work as well if you're not collaborating with people who get it and are smart and are conscientious and are just get the job done and are fun to be with. Okay, the surprise perks of field work. Do you see it? There you go. A desert tortoise happened to be on the job site out in the middle of nowhere in the Mojave Desert when we worked out there. We had an environmental guy keeping track of all that stuff. And I could go on and on about the fun things to see in other places. We take every job as an opportunity to spend one extra day in the area just to see how people live, see what might be in the area. We went to the Rock and Roll Hall of Fame when we were in Ohio. We went to this Hickory Run Boulder Field, which is a post-glacial rock glacier. We went to an Amish auction. We were driving through the middle of nowhere, and we saw that the twice-a-year auction was going on. So we stopped, and I'll tell you, those black buggies, they're expensive. And so the lower right is the three of us at the Carnegie Museum of Natural History in Pittsburgh. The top right photo is the Arboretum on Belle Isle in Detroit. Don't let anybody tell you that Detroit is a depressed place. That there is great stuff in Detroit, okay? And the middle, this is the 9/11 Memorial just outside of Newark, New Jersey. And I forgot the name of the park. Sorry about that. Anyway, this huge monument there, and you go up and read the plaque on it. This is a gift from the people of Russia and Vladimir Putin to the people of the United States of America to honor their sacrifice in the 9/11 crash. I mean, who knew? And then finally, what is all this about? Whether you're a researcher or just a worker or a curious person, everything is an opportunity to tackle a problem and try to contribute a solution. Am I splitting the atom? No, but pardon me. I hope I'm helping electric power plant constructors do their job a little bit better. Okay, that's it. Thank you.
Okay, question from the audience. I am looking at the online audience as well. So far I have not got questions. If there's any questions, I will ask you. They can come up. So actually, I'm an electrical engineer, by the way. So I will be one of the person that you are talking about. I'm no clue on the thermal property of the soil. So I'm curious to know that actually from the engineering side, how the data, how your measurement has impacted their design of underground cabling.
Oh, well, so far as I know, no one has been electrocuted at any job site I've worked on. Okay, that's a good thing. And it's too soon to tell on the thermal properties whether we're doing it right. So that's in the future to see if we're doing it right. Because it takes a while for these cables to overheat and melt. And if that starts happening, then I'm going to retire.
So I noticed that in the measurement, some of the measurement is done in a rather shallow layer of the soil and some is in depth. But those are the construction company tell you at which point you need to do them.
They do every time.
Oh.
Yep.
That's actually very easy.
I'm just kind of curious about kind of the scaling here in terms of oversampling versus undersampling. How coarse is good enough?
So on the at the within location, we just dig one pit. And the measurements that I take are probably 3 or 4 inches apart. Right. Whereas between locations, they're probably a quarter or a half mile apart. So big difference. But the variability over a few inches tells you that this is real variability.
And you see, well, undersampling, what kind of scaling are they using?
I don't, the people that are undersampling are literally taking one measurement at one location. Yep. So they have no idea whether that's a good, bad, or otherwise data point. And if nothing else, if I take 3 to 5 measurements, you know, I can start telling if I have a bad probe placement, or maybe this is a 10-centimeter probe, and if I push it in and I get a little bit of resistance, it might be hitting a pebble that gets pushed out of the way. And if it creates a void space, I get too high of a reading. So having multiple measurements at each location tells me it's quality control, for one thing, you know, and then the natural variability is a product of having those statistics.
So the water content impact your data significantly, right? On the soil. So you often pick the like sunny day or how the weather mess up with your measurement.
So when I sample at 30 to 36 inches depth, weather is really not a problem. Yeah.
Any other questions?
All right. Thanks, everybody.
Is the 30 to 36 inches down, is that standard? Is that usually what you're asked to do, or are you usually asked to do deeper or shallower?
So from the engineering point of view, the shallower